Inside are two pistons that bear on the brake shoes, a spring that positions sealing cups against the pistons, and a bleed air valve that lets you get rid of air in the brake system, as we're showing you here on another wheel cylinder. The combined area of the wheel cylinder pistons is larger than that of the master cylinder piston. So the force that the master cylinder piston applies is multiplied several times, adding to the force provided by brake pedal leverage. As the piston in the master cylinder puts pressure on the brake fluid, this forces the wheel cylinder pistons to move the brake shoes apart. We've exaggerated the action here so you can see what happens. Brake shoe springs return the pistons to their stops as brake pedal pressure is released. The piston cups face inward and so prevent brake fluid from leaking out. Now we're ready to look at the entire drum brake system and see how it operates. You can control the amount of braking power the hydraulic system will deliver, all the way from slowing down wheel roll to wheel lock by the amount of pressure you put on the brake pedal. Here's how it works. Remember that the brake pedal acts on the master cylinder piston the same way the lever acted on the piston in our hydraulic system demonstration a while back. The brake fluid is not compressible, so the further the lever pushes the piston, the further the fluid pushes the second piston. The same thing happens in the drum brake system. The result is that as pressure on the brake pedal increases, so does the pressure exerted on the brake shoes by the wheel cylinder pistons. Let's look at the situation using just one drum brake assembly, remembering that the same things happen at the same time at each wheel. This area is the braking surface of the drum. Actually, the gap between brake shoe linings and the brake drum is very small, but we're making it larger here so you can see what's going on. Let's say the wheel and the brake drum assembly attached to it is rotating. Now, let's push down on the brake pedal. The master cylinder piston transmits force to the brake fluid in the brake line and in the wheel cylinder. Both pistons are forced outward against the brake shoes, and these in turn are forced into contact with the brake drum. The friction between the brake shoe lining and brake drum begins to slow the wheel down slightly. Now, let's push down harder on the brake pedal. Because the brake fluid can't be compressed, it transmits this increased force against the wheel cylinder pistons, increasing the pressure against them. The wheel cylinder pistons push harder against the brake shoes, the brake linings harder against the drum, slowing the wheel even more. The master cylinder piston will increase pressure high enough to cause the brake assembly to slow the wheel to full stop or wheel lock. Releasing the brake pedal lets the return springs pull the brake shoes back from contact with the drum and drive the pistons back to their stops in the wheel cylinder. The master cylinder piston, driven back to its stop, allows pressure in the system to decrease, but the residual pressure valve closes, keeping just enough pressure in the brake line and wheel cylinder to keep its sealing cups pressed against the pistons. These face inward, so no brake fluid can escape from the system. If there's a lot of repeated braking action, the friction between brake shoe linings and drums will generate excessive heat. This heat can also heat up the brake fluid in the wheel cylinder, causing it to expand back up the brake lines to the master cylinder, where it later returns to the reservoir through the compensating port. Now, let's say some air is trapped in the brake line near a wheel cylinder like this. Air is compressible, and that can cause problems. Let's again push down on the brake pedal until the brake linings make first contact with the brake drum. So far, so good. But now, let's push down harder. Here's where the problem shows up. The increased pressure in the brake fluid presses against the air bubble and it shrinks. Let's say the air bubble gets forced into the wheel cylinder. Plainly, the full force generated by the master cylinder piston is not being transmitted to the wheel cylinder pistons, and brake pedal action feels spongy. It takes a lot more pedal pressure to bring the wheel to a full stop, and the air can cause uneven vehicle braking. That's why it's so important to follow directions in the manual for bleeding air from hydraulic brake systems anytime you work on them. There's something else going on in a drum brake system you need to know about if you're going to really understand how this system operates overall. When drum brakes are applied, both shoes initially contact the drum with equal pressure. This is the reason why the space on each side of the anchor pin is equal. However, friction between the rotating drum and shoes tends to pull the shoes around with the drum. When this happens, one shoe is forced farther away from the anchor pin. This in turn forces the other shoe tightly against the anchor pin. Increased friction at this point tends to make both shoe assemblies pivot, using the anchor pin as an axis. If the drum were not present to contain the shoes, the action would look like this. Since the drum is present, the shoes are forced into tighter and tighter contact with the drum. This is what is meant by the term self-energizing in reference to brake systems. This action thus multiplies the force of the brake shoes on the brake drum. One more thing you need to know about drum brake operation. You'll remember we said brake linings will wear with use. The brake pedal then has to travel farther to force the brake lining to make contact with the drum. To close this gap to normal, you'll be using an adjustment tool to rotate the star wheel on the adjustment screw. This will return brake pedal travel to normal. Excessively worn brake linings will of course have to be replaced so the shoe doesn't score the drum surface. The components and principles of operation for the drum brake system on the M151 are similar to others you might come across, and also to the drum brakes used on the rear of the M880. In part 1 of this program, we've reviewed the basic principles of hydraulic systems. The fact that liquid is not compressible and occupies the entire volume of its container. The fact that force applied acts in all directions. And the fact that force applied by one piston is multiplied by the areas of the others. We then reviewed the major components of a drum brake system: master cylinder, wheel cylinders, drum brake assemblies, and talked about the principles of operation of components individually and as a system. If any of this got past you the first time around, don't feel bad, but give it another shot. Look at the program again as often as necessary to get a handle on it. In Part 2, we'll concentrate on the major components and principles of operation of the disc brake system used in the M880 vehicle.